Hello everyone, this is Keshav Peswani and I'm back with another chapter in the database learning series, which is Mastering and Understanding the Architecture and Data Storage of SQL. SQL, as we know, is the language that unlocks the potential of data manipulation, allowing us to draw insights from the vast digital landscapes that we navigate every day. Almost all the organizations in this world would be using SQL. But as the consumers of SQL, do we really know what happens behind the scenes when we send a query to SQL? In this talk, we would delve deep into the inner workings of the SQL databases, and we'll see what are the unique properties that can set them apart for their efficient operation. Now let's start with the architecture of the SQL. The architecture of the SQL is divided into three parts. First, or the top layer being the client. The second layer is the server layer, which is called the brain of the SQL. And the third layer is the storage engine wherein the data is stored. So it is called data storage. The client actually, if you see, interacts with the SQL Server engine directly from here to here, and it is responsible for authentication and security. The server engine, as we know, is the brain that actually formulates the query into an execution plan that can be sent to the storage engine for the retrieval of data. The storage engine is the place which actually keeps the data. So this is the place wherein the data is stored in the file system, but in a very efficient manner. And the results that the storage engine sends back is actually sent back by the server engine to the client. Now let's see what happens when a client sends a query to the server. Now let's say I'm a client and I send a query of this type, like select star from table 1. Once a query is sent from the client to the server, it is first checked in the query cache, and if the same query exists in the query cache, the result is sent back to the client without any further steps. If not, the query is sent to the query parser, which actually reads this query and forms a query execution plan, which is a list of instructions, and passes that to the query execution engine. The query execution engine actually calls the storage engine APIs and passes the list of instructions for the retrieval of data. Once the data is retrieved, it is sent back to the query execution plan, which in turn passes it to the query cache and hence back to the client. So this is what happens when a query is sent from the client to the server. The results are sent back to the client. We already went with the layers, and we already went what happens with when the query is sent from the client to MySQL. Now let's dive deeper into the architecture of the SQL Server engine, how it exactly forms the query plan, and what are the steps in forming that query plan. So let's say we are the client, or we are the actors in this case, and we send the same request or the same query as select star from table 1. As soon as the query comes to the server, it is first checked in the query cache, and if the result of the query exists in the query cache, the result is sent back directly without any further steps. However, if the result of the query does not exist in the query cache, it is sent further to the query parser. The query parser uses the MySQL's grammar to interpret and validate the query. For instance, it ensures that the tokens in the query are valid and are in the proper order, and it checks for any mistakes that happen in the quoted strings. So once this is done, the query parser would convert this query into a parsed tree. This parsed tree is then passed to the query preprocessor. Over here, it's just checking the tokens and literals. But the query preprocessor checks this parsed tree for any additional semantics, such as like it'll check for any table or column names, existence. It will also resolve any name and aliases to ensure that column references aren't ambiguous. It also checks for privileges. So the user that is using or calling the SQL server, does it have the right privileges to query this particular table? This step is generally very fast, and the parse tree is then passed on to the query optimizer. This parse tree is now valid and ready for the optimizer to turn it to the query execution plan. A query can be executed in many different ways and still produce the same result. The optimizer's job is to find the best option. MySQL uses a cost-based optimizer, which means it tries to predict the cost of various execution plans and chooses the least expensive one. The unit cost of a single random page is 4 KB page read. So this thing is the least expensive. This query execution plan is then passed on to the query execution engine, which in turn calls the storage engine API to get the results back. So this is done by API calls, and the result is sent back to the query execution engine, which in turn is set back to the query cache, and if the result is in a cacheable state, it is cached out. Otherwise, it's sent back directly to the client or the actor in our case. Now that we understand the in-depth architecture of SQL, let's see what all unique properties are there at each step during this entire execution of the query. The MySQL client server protocol. The connection between the client and the server is managed by this client server protocol, and it is a half duplex connection, which means that it can only send or receive messages at a time. The query that the client sends, it can be sent as a single packet. There is a property called max allowed packet, which tells us how much data we can transfer as a query at a given time. If the query is larger than this max allowed packet, then it will fail and the error would be sent back to the client. The response that the client receives, it is in multiple packets. The client receives the entire results set only, and the client cannot stop the server from sending the data back. Hence, there is a need for the limit. So that is the reason we should always use the limit option while querying the SQL, because we cannot stop the operation in between. Now the execution path of the query. We had seen earlier that there is a first step is the cache check, wherein if the result is found, then it is returned directly without any further steps. But in case the result is not found, there is the parsing and the optimization step. As we saw that the parser is meant to break the query into tokens, the preprocessor checks the semantics, sees whether the table or the column exists, resolve aliases and the privileges, and the optimizer is the one that chooses the best execution plan based on the cost estimates. The execution plan is nothing but list of instructions for query execution engine. The query execution engine follows or iterates through this list of executions and calls the storage engine through the APIs. This is all what we had seen previously when we were going through the in-depth architecture diagram. The results that are returned back to the client are returned in an incremental manner. That means as soon as the results are generated or the rows are generated, it is sent back to the client. One of the most important things to see over here is the query optimization process. This actually determines how is the performance of your MySQL server in turn. So there are various things that we need to keep in mind for the query optimization process. The query optimizer is a cost-based optimizer, which means that it would estimate the cost of the execution plans and will choose the least expensive one. And the factors that affect this cost is the pages per table or the index size, the cardinality of the index, the number of rows, and the key distribution. How evenly the key is distributed or how is the cardinality of the key. But there are certain limitations that the optimizer has. The statistics could be wrong. The server relies on the storage engine to provide you the statistics, and they can range from exactly correct to widely inaccurate. For example, the InnoDB storage engine doesn't maintain accurate statistics about the number of rows in the table because of its MVCC architecture. This doesn't help the optimizer in calculating or getting the right number of rows that are there in the table. The cost metric is not equivalent to its true cost. It's just a pre-calculation to the actual cost that would happen when the query runs. It doesn't consider the concurrent queries or the parallel queries that are running on that particular table. If there are multiple queries running onto the table, performance of that table would be impacted, and that is not taken into consideration. Also, the operations outside of the query execution plan is also not taken into consideration. When I say operation, I mean the stored procs or the user defined functions. And it may or may not find the optimal plan in every case. So it's just based on certain factors, but it may not find the right optimal plan. In order to get the execution plan for a query, you can call this query explain extended and give your query followed by show warnings. Now let's see what are the different types of storage engines that are available in the MySQL. There are multiple storage engines that are available in the MySQL, the major two ones being the InnoDB and the MyISAM engine. And there are others as well, like CSV engine, in-memory engine, but these two are the major ones that are widely. The InnoDB engine is MySQL's default transactional storage engine, as well as the most important and widely used. It was created to handle a large number of short-lived transactions that are normally completed rather than the rolled back ones. It's also common for non-transactional storage because of its performance and automatic crash recovery. It also has a lot of optimizations. Predictive read ahead for pre-fetching data from the disk, an adaptive hash index that creates hash indexes in memory for very quick lookups, and an insert buffer to speed inserts are just few of them. The MyISAM engine, which was MySQL's default storage engine in versions 5.1 and prior, offers a wide range of capabilities, including the full text indexing, compression, and spatial functions. The transactions and the row level logs are not supported by MyISAM engine. The fact that it isn't even close to being crash safe is arguably its greatest flaw. That is why, more than a decade after gaining transactions, MySQL still has the stigma of being a non-transactional database management system. Once the results are returned back from the storage engine to the execution engine, it is sent back to the client via the query cache. So the cacheable queries are stored in the query cache and the results are sent in an incremental manner. This helps us in two ways. First, it reduces the memory pressure because there is no data being stored in the memory, as well as it starts providing the results to the client at the earliest. The SQL databases exhibit unique properties, including the query engine, which is very powerful, the transactional capabilities via the InnoDB engine now, and the diverse storage options, which is through InnoDB and ISAM, an archive engine, in-memory engine, CSV engines, and many other things. So this was the architecture of SQL. Thank you for joining in the enlightening journey into the depths of SQL's architecture. I'll see you soon in the next video wherein we'll see the architecture of various NoSQL databases such as Mongo, Cassandra, and Graph databases. Thanks a lot.